Hello, in this unit we're going to be looking at Bohr's model of the atom. Now I have a couple of examples of Bohr's model of the atom here, and what I want to stress is that this is Bohr's model of the atom. We don't really know what the atom looks like, but this is what we believe the atom looks like based off experiments. And what I want to do in this unit is show you, well, why is it that we believe that the atom looks this particular way? So we have the nucleus here in the center. Remember, this is just a representation of the nucleus. The nucleus will be very, very, very small. It's only written this way so we can see that the protons and neutrons are there. And then you have these electrons traveling on these energy levels. So why is it that we believe that the atom looks this particular way? To answer that question, we need to know a little bit about light. Now, light is just radiant energy. Just energy that's going through space. It doesn't need matter to travel through. It just travels through empty space. Light is also referred to as electromagnetic radiation. So the reason why it's called electromagnetic radiation is because it has an electrical component here as well as a magnetic component, as you can see on the green, and they are perpendicular waves to each other. Light also is usually what we refer to as what we see, so we usually see light, but we'll see that there are many different versions of light, not just the version that we see. So let's look at the parts of a light wave. The two main parts of the light wave that we kind of want to look at in this unit is wavelength and frequency. So let's start with wavelength, and I'll refer to wavelength as lambda. It's a Greek letter, kind of looks like an upside down Y. And this is just the distance of one wave. So from the top of this part of the wave to the top of the next part of the wave, that distance there measured in meters is the wavelength. Then you also have frequency, which is just a cursive V. And this is just the number of waves per second. So let's say this is second 0, this is second 1 here. However many waves you have in that particular second, that time, is the frequency. So we can look at these two different waves and compare. The wavelength here is larger, wavelength here is smaller, and then the frequency here is larger, and then the frequency on this wave is smaller. So let's look at the relationship here between wavelength and frequency. So the relationship between wavelength and frequency is an inverse relationship. So there's an inverse relationship. That just means if one thing goes up, the other goes down. It's kind of like a seesaw. So if we look here, as the wavelength decreases, so the wavelength gets smaller from this wave to the next, the frequency, how many waves you have, goes up. So wavelength, so we have as wavelength decreases, the frequency increases. The opposite is also true. So as the wavelength increases, the frequency then decreases. And this just kind of makes sense. If you have a longer wave, you can't fit as many waves in that time frame. If you have a shorter wave, you can fit more waves in that time frame. Remember, this is a time frame of 1 second. What I want you to kind of see here is that both of these waves are traveling at the same speed. And that's the speed of light, which is c. And this is equal to 3.0 times 10 to the 8 meters per second. And this is just a universal constant. It's never going to change for us. We're going to just always use the speed of light as 3 times 10 to the 8th meters per second. And even though that this has a higher frequency, both of these waves are moving at the exact same speed. And that can be written mathematically like this, where c is equal to lambda, wavelength, times the cursive v here for frequency. So even though wavelengths, or the waves, travel at the same speed, there are differences between the two waves, wavelength and frequency, and these differences allow there to be different types of light. And all the different types of light is called the electromagnetic spectrum. So the different types of light are based off of the wavelength. So a big wave, like one that's 1 kilometer, is a radio wave. And the radio waves, we can send signals. That's how you can listen to music from a radio. That's how you can watch TV. All those signals are sent through a radio wave, which is a light wave. You have microwaves, infrared. Visible light is the light that we see, and it's only a very small portion of the whole spectrum of light. There's ultraviolet light, that's the light that kind of gives you sunburns, X-rays, and gamma rays, which are very, very dangerous. So what I want you to see is that the different wavelengths of light give different types of light. And this is also true for the visible spectrum. If we look here, the wavelength slowly changes here. And each little change in the wavelength gives us a different color. And what we need to realize is that each wavelength is a specific color. So every time the wavelength changes slightly, the color of the light also changes slightly. And that's going to be very important when we start talking about the experiment that prove, or that we are basing the model of the atom off of. So the last thing I want to leave you with here is this duality of light idea. That light acts both as particles and waves. So not only does it act like a wave, like we're used to seeing like in this video, it also can act like a particle. And the particle is called a photon, which is a particle of light or a quantum of light. And we'll look more at this idea in class, so just kind of write down the definition, and we'll talk more about light in class.